Howdy, everybody. Hope you're doing well wherever, whenever you are. We're here for Advent of Code Day 10. Hopefully, my sound and recording's okay. Had some struggles getting it working this afternoon, I guess. Anyway, we're here for Day 10 of Advent of Code. We only have 2 days left after this one, which is kind of crazy to think about, but I've had a lot of fun. This day, though, was, it was still fun to solve and finally get the right answer, but it was a lot of work. And I struggled enough on part 2 that I asked AI for a hint to kind of help me. So I'll walk you through that process of how I got there. And yeah, how you get to it. So I think let's just get on with the day, and uh we'll talk about what happened. So the problem is like you finally you're still going through these different rooms, I guess, to help decorate and do the stuff, and you're in a large factory this time, and they have plenty of time to decorate, but all it's because their machines are all offline, so they can't start them up. And the way that the machines come on is like you're basically gonna, for part 1 you're gonna play a lights out game, and then you're gonna play for part 2 a lights out game, but with like intensity. So I don't know if you've ever played a lights out game before. It's kind of a lights out game, but like if you imagine a square grid, you have like lights that are on and lights that are off, and every time you like push one of the lights, it like alternates turning them on and off. In this case, you're not doing that. You're pushing a button, and that turns some of the lights on and some of the lights off, or sorry, it like toggles some of the lights anyway. So the point is, for part 1 you gotta like get the right, you have like this diagram that says here's what the buttons do, and like here's the things you need to do, and once presumably you get the lights to the right place and then the joltage to the right place, it will bring the machine online. So that's what you're trying to do. So they give you some input like this, and these are the buttons. So you can imagine there's 1, 2, 3, 4, 5, 6 buttons, and each of them say they toggle, or in part 2 they like increment one of the lights on the thing. So by pressing number 3, what it's saying is go to the index 3, so the 4th position, and turn it on. And for this one, go to, it will toggle positions 1 and 3. And this will toggle position 2. And what they say is your goal is to get to this position, right? They want the lights to be at this position. And then in part 2, they want the joltage to be at this position. So you can kind of see there's like 1, 2, 3, 4. So 0 index would be 0, 1, 2, 3. There's like 4 total positions, and you need to like press these buttons in such a way that it ends up with this, meaning like the 2 middle are on and the 2 outer are off. And you kind of like, if you've ever done these puzzles before, you kind of like start to find patterns. I don't know if you know if you've done this before, and then you can solve it. And so that makes them kind of fun, is like finding the patterns and getting to positions where you can figure it out. The one thing you run into, though, is like, how do you do this programmatically? Right. And what the question is actually asking is not can you get to this state, but what are the fewest number of button pushes you can use to get to the state, right? So you could probably press all of these thousands of times and eventually get to one of these states. It wants to know the fewest. So how does it kind of gives you an example. Like given this first example, you could push these 3, it says a total of 3 button presses. First buttons on once each, a total of 3 button presses. So, right, you could press this, which would turn on 3. This one. You could press this, which would turn on 1 and then turn off 3, and then this one would turn on 2, and that would get you there, right? So that's essentially what's happening there. And but that one takes 3. The smallest number I think for this one is 2, right? If you just press the oh yeah, you press 0, 2, and then 0, 1. If you press these two right here, you see how it toggles these two on, and it toggles the 0th one on and then off again. So that's what it's trying to say, is how do you well, that's what part 1 is trying to say. How do you get that? Then part 2, you're doing a similar thing. We'll talk about it more, but you're just going to use these joltages where you're like every time you push a button, it increments the intensity, and you're trying to get there. So, well, how did I solve part 1? Part 1 was actually, you know, if you've done BFSs before, it's not that bad, at least in my mind. Like, the puzzle seems difficult if you think about it, like at a very high level, is like, oh, how do I find the best? The thing that got me to a solution pretty quick was like, oh, well, I can just my neighbor function is where am I at right now, and what happens if I press each of the buttons. And if I do a BFS style where I'm always trying all the values from all the buttons, presumably I get to the shortest state rather quickly, right? Like if there's only 100 presses, I just try, or sorry, if there's only like 5 presses, I just, you know, try each of them 5 times 5, and somewhere in there I will have gotten a good solution, right? Again, the way a BFS works is you're going to try all of the first buttons, and then for all of the neighbors of those first buttons, so it is going to multiply a lot, you're going to now try all of those, and eventually you get to this state relatively quickly. In fact, you can see for part 1, for all the buttons, the total was 486. So like that, you aren't trying a lot of button pushes, if that makes sense, to get there. So that's all of that I did. And so here's my code for part 1. It becomes less interesting, or it becomes crazier for part 2. But what do we do? Ignore the epsilon. That's for part 1. Part 2. I didn't move this around, but we're just going to parse all of our lines into a machine. The lines are a little complicated, right? So we have to like, it felt good to create like a little struct of the machine and like parse those lines. So we just parse them. For the lights, we strip out the brackets. I don't know why that name went out of my head. And then we rev and fold. Oh, I should say for the lights, I'm using a U size. So we're doing bit mask stuff, right? So I do a rev specifically here because we want to be able to calculate, compare it to a value that I build below. Maybe I should note that. So we're going to get some number for this lights, you know, and it's really just toggling of the bits, right? The idea is what I'm going to do is instead of my lights being dots and hashes, they're going to be like, you know, I'm going to have a 0, 1, 1, 0. This is what I'm looking for. And then I'm going to start with like this state, and I'm going to say, what are my neighboring states? And it might be 0, 1, 0, 0, and 0, 0, 1, 1, and 1, 0, 1, 0, and a few other states, right? And I'm basically just going to BFS until I find this state. Hopefully that makes sense. So you could have used a vec bool here. That may have been more readable. And in the end, I don't know that using the bit mask helped, but it was something I thought, oh, I can use a bit mask here. I've been practicing it. Let me practice it here. Then we just collect the rest of the parts. We know the last one is the joltage, so which we'll use for part 2. So we strip out the braces, split by commas, get the integer values. The rest of the buttons are the rest of the parts are the buttons, which we split by or remove the parens, and then we split by commas, right? So you can, a lot of this here is just me copying and pasting a lot of stuff. I have to give this a thing. It's so crazy. Like, I think I understand why the Rust compiler, or the Rust, yeah, the compiler is saying, oh, I don't know what this type is. And it's because here I have to sort this time. But I don't know if you remember a previous day, I didn't have to tell it and it kind of just figured it out. And I think it's here because I have to sort, right? So it's like, oh, I kind of need to know what this is if I'm going to sort. Sorting here actually helps, and I don't totally understand why. Like if I remove it, the part 2 is actually slower. And I think it has to do with how we're solving part 2. It doesn't really affect part 1 though. But anyway, we sort the buttons. You'll see why in a minute. But then once we've got that, now we can like parse each of the machines, right? So we're going to parse, we'll get a machine, and for each of the machines, we're going to do a BFS, right? I have this 0 here. Sorry. I'm very, my code probably isn't up to snuff of what it usually is, because I spent a lot of time on part 2, and I kind of like part 1 was just like a throwaway for me. So, but again, how are we going to BFS? We're going to start with our 0 value. So all the lights are off and we've done 0 moves, and we're going to add that to our scene list. So if we ever get there again, we know, there's no point in trying that one. But then we're just going to go through our list. And if we ever found, or go through our frontier, if we ever found what we're expecting, then we know we're done and we can return the distance. Because we've done a BFS, we know it's the smallest, so we're done. Otherwise, we try all the neighbors. And what are the neighbors? It's just every single button. And the neighbor is, again, we're just going to fold with our current lights. We're going to XOR it with each of the values in the button. So this is a cool way of like toggling. The way to think about it is, like we go here, like assume we have a 0, 1, 0, 1, and we want to toggle like this value right here. XORing will toggle it, right? What we'll do is we'll create a mask like 0, 0, 1, 0, and we'll XOR this thing. And the way exclusive OR works, right, you can see right here what we're doing. We're XORing what we currently have with this kind of mask right here. And exclusive OR means I kind of have to, let me think about this for a minute. Oh, we're doing it for each of the buttons. Yeah, so it only switches them if they're, wait, what? How does that work now that I think about it? Or neighbors fold. Did I get that wrong? The idea behind XOR is it's like it produces 0 if they're the same, 1 if they're separate. So I'm actually trying to think of how this works. I have some number of lights. I'm going to XOR it with my movement. Is that still, do I still have the right answer? I'm so jolted by today. We start out with our current light and we XOR it with 1 right shift N. So like 3, and we do that each time. I actually think that might be a bug. I don't know how it's getting the right answer. Someone correct me if I'm wrong, but like if you XOR these two values, right, this is going to produce a 0, 1, 1, 1, right? Like XOR produces a 0 if they're both 1 or both 0. So, or a 1 if they're not. So, but this is not what I want. Oh no, it is what I want. Yes, it is what I want. Okay, so it does work. Sorry, my mind is blown. This is exactly what I want. If we're toggling this bit, we now want it to be 0, 1, 1. And so you exclusive or, you say, oh, these are the same, so it's 0. These differ, these differ, these differ. Yeah, I think that's right. Okay. Yeah. So the thing is if this was already a 1 and a 1 would make this a 0. Okay, so I did have it right. Okay. Anyway, this is all to say, essentially what I'm doing is I'm like turning on and off lights based on what the button press changes, right? And then I just add it to my list, or I check to see if I've seen it before, and if I haven't, I add it to my to-do list with an additional distance. I just do that over and over again until I find the light position that I'm expecting. Like once I've found the light position I'm expecting, now I've found the solution. This is just a BFS, right? We've done this before. It can be hard, so please, if you haven't done it before and it doesn't make sense, don't worry about it. I have previous videos, but maybe sometime I feel like it's probably good to re-explain these every once in a while. I'm not going to do that today, but a BFS is a very good solution for like finding the shortest path. And in this case, if you think about what we're doing, we're like finding the shortest path to turning on to making the lights be the exact configuration that they're expecting. So, and that solves it, and it solves it pretty fast. Is it the most optimal solution? Probably not. You might be able to use DP to solve it faster, where like you prefer button position. You look at how button positions solve, and then I don't know. I actually think BFS is more than sufficient. So I didn't even try or think about any other solution. Okay. Okay, part 2. What happens next? This is where it gets crazy, people. So yeah, they say in part 2. Let me get there. Great. Now you figured out the lights. Now you need to figure out the joltages, and these are numeric counters. And each time you push a button, it increments it. So the idea is now instead of just like turning on and off lights, you're now every time you push that button, it's going to increment that value by 1, and you need to get it to the exact configuration that it's given. So 3, 5, 4, 7. So now instead of like I can't use a bit set anymore like I was before, right? I was just using this set to like search this space. I now need I start with 0, 0, but like this one will be 1, 0, this will be 0, 1, 1, but the next ones will be like, you know, this space might be 0, 2, 0, 0, and this one might be what is it, 0, 1, 1, 2, or something, 0, 1, 1, 1, and this one might be whatever, 1, 1, 1, 0. And then, you know, as you keep going, now you're getting like a 0, 2, 1, 2 or something like this, right? I hope that makes sense. Is now we can't really track it as a bit set because we're slowly incrementing the numbers. The problem with this is now the solution space is just huge. So my naive brain kind of was all like, oh, well, what if I just try a BFS? I'll just BFS, but now I'll use a vec U size and I'll just count. And you can do early termination, right? Obviously, if you ever exceed some value that you're expecting, right? Like if you're looking for a 5 in the second position and you get a 6, you now know you've gone too far. But the solution space is just huge, right? You're never going to find it. So I also tried it with DP, right? I said, oh, could I DP it? And I was like, this just isn't working. There's got to be some other way to do it. So I looked at the input and I was trying to look for patterns. I'm like, oh, is there a pattern? Like, what if we pick like the largest one? Can we like, is there some trick to it where we're saying, oh, if I pick 2 specific values, it like increments them perfectly, if that makes sense? That, at least from what I could tell, it doesn't. So, you know, maybe I missed that as well, but I couldn't really find a pattern. So I went to AI to help, and I'll show you my AI talk with it so you get a kind of idea of what I was doing. I didn't want it to just solve the problem for me, right? Because I don't feel like that's helpful. So I kind of looked, I asked it, I'm like, hey, I have this puzzle. And I kind of explained the way the puzzle works. And I said, hey, so I solved the part one, which is great, but I can't solve it for part two because like the numbers are very, very large. And so, as opposed to just toggling, doing a lights out thing, I'm now doing like this increment and it's like very large. And so I'm like, can you give me some pointers of where to look? And what did it say? It's like, this is a classic pivot in algorithmic thinking. You're moving from graph theory to linear algebra. And that's once it said linear algebra, I'm like, oh, I'm such an idiot. And so I knew I could solve it at that point. Uh, uh, but it was not hitting me. So, but until it said this. And so I talked to it. Well, I kind of understood how to solve it at this point, but I did like need I think I needed some coaxing into it. So you can see it says, oh, kind of the way to think about it is you do a Gaussian elimination, which we'll talk about in a second. And then that's going to give you your list of like free and like non-free variables. And from there you can solve the problem. So that's what we're going to talk about. Again, I want to show you like sometimes I don't have the answer and I'm still learning. I'm trying to get better. And so I think it was useful to talk to AI in this way. I didn't want to just, I didn't copy and paste and want to solve the problem, right? Obviously, if you're, want to do that, that's fine. Especially if you're still not getting it after the fact, right? Like after this, if I still didn't get it, I would, I think it's fine to say, can you help me solve the actual problem? And then we can walk through the steps to understand the process, right? So there's days in past where it would have been nice to kind of have like this quote unquote hint giver that can like step through the thing to help me understand. Because I think that's the key. If you can't solve a problem, go look for a hint. Once you get the hint, for me, it was linear algebra. Then once you get the hint, try and solve it. And if you still struggle, go look for further hints or go look for other solutions. Figure out how it works. But I want you to like spend time understanding it, right? Once you understand it, then the next time it comes up, hopefully, you'll be better. I don't know why this one can't strike linear algebra to me. I must have been missing how like what the relationship to the buttons and like the solution was, but like once it said linear algebra, I'm like, oh, okay, we can solve it. So what we're dealing with is, it even says right here, a system of linear equations. And you can see I actually kind of did the math here. So this is the example input, right? And what I'm doing is I'm turning each of the buttons into a column. So this button was, just said it was 0, and this button was 1, 2, and this button was 3, and it was 0, 1. This button was 3, and then this button was actually that's not right. These are not the right values anymore. Because I actually pre-sorted them according to what we're going to do is try and solve a system of linear equations using putting it into row echelon form via Gaussian elimination. And so I had already done the pre-steps. So I don't think this is right, because I think what was the original puzzle input? It wasn't 7543, it's 3574. So this is actually out of order. 3 5 7, so 3. If it was in what I should, maybe the best way to say it is, well, should I try and draw it really quick? 3 5 7 4. So 3 1 3 2 2 3 0 2 0. So I would start it creating a matrix with that, right? So 0 1 2 3, and then it would be 1 3 2 2 3. what's the last one? 0201. One more time. 373547. We'll get there, people. Sorry. Okay, so I built this. What I do is I build this matrix, right? And again, the columns, so the calls are equal to the button presses. And that is to say, when I press this button, it's going to turn on the third one. When I press this button, it's going to turn on the first and third, and so on and so forth. And now we're going to do, we're going to try and put it into row echelon form. Maybe the way to think about it is, if you've ever tried to solve a system of linear equations, you eventually want to get to something that's like 1 0 0 0 1 0 0 0 1, and then like 5 7 9. So these are zeros. I apologize if they look like sixes. The idea is, if this is like your x0, x1, and x2, you now have solved this problem. You know that x0 equals 5, x1 equals 7, and x2 equals 9, right? You're trying to get to that form. You can't always do that. Some problems have multiple solutions, which most of these ones do. I did look briefly how many dependent and independent variables there were, or free and fixed variables, and like there were some of them that didn't have any free, which means there was an exact solution that you could immediately determine, but most of them did not, and so you kind of had to figure this out. So the goal is to look, this is what we call row echelon form, where we have like this kind of diagonal of ones and hopefully all the zeros. In our case, we're not going to get a bunch of zeros, but the goal is to get to here. And you use Gaussian elimination to do that. And how do you do it? Well, first you can do operations on the matrix. You can always swap rows. So you always want to swap a row so that like you get like this structure the easiest. And then you can do operations on the matrix. So you can subtract rows from each other. You can multiply rows by scalars, or by that matter, divide rows by scalars, to get you to a point where you look at a thing. So when you solve it in your head, if you've ever done linear algebra, you can kind of do things like, oh, so I want to put this one at the notice I want to put this one at the top because it has a value there. And then I want to put, so this should be the first row, and then this one has a value in that next position, so I want to put that there. And then this one has one, so this one should be 3, and then this one should be 4. The idea is like I've kind of like sorted them, and so now I've sorted them and I have this, and now I can do operations. So how do I make sure that well, this one's already in the right place. This one's already in the right place. But notice there's a 1 up here. I want to turn this 1 into a 0 if I can. And so what I'm going to do is subtract row 0 from row 1, and that will like give me the proper format. So that gives me this next one right here. And so now I have this solution right here, right? And this is all to say we're just doing Gaussian elimination. If you don't know what this is, I'm sorry. I'm not good at explaining this stuff, but the idea is it's an algorithm for you to solve a system of linear equations. And that's what we're trying to do for this problem, because once we can like figure out what the system of linear equations, the solution is, we can now start kind of guessing with any of the free variables that we have. And I'll show you how that works in a minute. So we're going to do this, and we know this. So now we've figured out these two. We need to figure out this third one. It's actually in the good. This is actually okay. I guess it's technically 0, 1, 2. This 2 is okay. Now we want to figure out like this third position. And oops, there's no third position here, right? So we know that x equals 3 is like, we can't actually like solve for it using this row echelon form. It's considered a free variable. We can't get like a fixed value in our list, or it's independent is what it's also called, right? So we'll skip 3 and just mark it as, hey, we know this is something that we can tweak to get us to a solution. If it's not, because we now know we're not going to get an exact solution, we know we can tweak these numbers to get to the solution we wanted. And there's a key to this in the puzzle after I reread it, after doing this, that kind of leads you to down this path too. So I'll show you that in a second. Anyway, you kind of, so now we try the fourth one, and you see we can subtract these two rows, subtract this row from this row to get like this thing right here up back into its place. So we do that, and that gives us this number. And now we've run out of like equations, and so that we can't ever solve for the fifth one. So we now know the fifth one is a free one as well, right? So we now have like two free variables. That is to say, we now have two variables that we don't kind of fit into the thing. There's no single, maybe the way to say it is there's no single solution to this answer. There's multiple solutions to the answer. So what you have to do is just figure out what those values are. Essentially what happens is this, now we can turn back into this, right? So basically wherever there's a value, we now put that in there. So x0 plus x3 minus x5 equals 2. And then here and here and here. So this is our like new set of equations that we're interested in working on. And we know that x and 3 and x and 5 are the interesting ones, right? So if we go look, you can see each of the equations have x3 and x5 in there. So what we need to do now is kind of like fudge with those x3s and x5s and find values where all of these equations are kosher. They work, right? We need to find all the values where the equations work. And then that will help us figure out how many times we need to press the buttons. Okay, the hint. Where is the hint? Somewhere in here it says, oh, right here. You have to push each button an integer number of times. There's no such thing as 0.5 presses, nor can you push a button a negative number of times. Okay? So that's interesting, because if you're looking at this like this new system of linear equations, you could have all kinds of answers for these values, but it might be like x3 equals -5 and x5 equals 3.34 or something like that. Some weird numbers, right? Actually 3.4 is not probably possible, but it may be like x5 equals 3.5. I actually don't know what they are. There's potentially an infinite number of solutions. So is that, yes, if you can go negative, there are infinite number of solutions. So there's no like one true solution to most of them. But now notice though, what we've done is we've taken, we've taken like 5 values times like 90 plus options each, to now we have 2 values with maybe like 20 to 30 options. And now this is a much simpler space to search over, right? So that's where, once you've done this part and now you know this, now you can do kind of like a DFS or a DP to say, how do I solve for this small thing? And that's kind of the hint I needed. Remember, I told you I kind of started with a BFS. It was clear that wasn't going to work. I hadn't even solved the first one. And so I tried it with DP, and I don't think I had even solved the first one before I gave up. And I'm like, okay, that one's clearly just not going to work. I got to find something better. So I looked at the input. I did some looking to like try and figure out how I might optimize my DP and stuff like that. That's where I asked for the hint, and it said system of linear equations. So now I can take my I have to build I have to solve this gobbledygook right here, right? I have to do all this gobbledygook. But once I do all that gobbledygook, I can now just BFS over a smaller state space, right? There's a fewer number of branches, so it's more likely that I'm going to come to a solution quicker. And in fact, I do, right? Over, I don't know, there's like 100 of them or something. I can solve them all in like 5 milliseconds. So, I hope that makes sense. I want to make it. We'll walk through the code. If you don't understand any of this, it's okay. Some of it's still a little nebulous to me, right? Like, obviously, I've taken a linear algebra course, so if you haven't, you're probably just saying, "What the heck are you talking about?" this whole time. Maybe you've solved systems of linear equations, right? Like, have you ever in math class you had like, x plus y equals 12, and I don't know, 2x minus 4y equals 50, something like that. And you're just like, can you figure out what x and y are? And it will either be like, x equals n and y equals m, some two values. I don't know what they are for this one. It may not be solvable. Or it could be like, oh, there's no solution. Or it could be like, there's an infinite number of solutions, right? And like, it maybe, so it's quite possible that if you're watching this, maybe you're in high school, you've done this kind of math at some point in high school or whatever. Well, linear algebra is just a way to do that with like higher order things, many more solutions. And Gaussian elimination, which I guess I'll have a link in my code, is an algorithmic way of doing that. So we can turn into intuitive things, right? So me ordering it and then me figuring out what these things should be to like get it into its row echelon form. That's just, it's an algorithm to do what like you intuitively might do if you were solving any other algebra problem. This one just happens to be linear algebra. But then once we get to this, now we can just DFS it. Okay, so let's look at the code. How does this work? Well, I'm going to create a matrix, and I'm going to use F64s. That's what this epsilon is for. Because I'm doing division and stuff, I may not get an exact value. It may be possible to do this with integers, but I've always done this stuff with F64s or F32s, or what, floating point numbers, because you're doing like division and stuff, and you often don't want to truncate. So anyway, in the end, you end up with a correct number, but like the only thing you have to do is that you just have to check, does this like quote unquote possible solution fit into the requirements of, I have to press an exact number of times, an positive integer number of times. Okay, I'm going to track my rows and columns of my matrix because I use them all over the place, and these are my independent and dependent variables. Dependent are the free variables, or no, those are the fixed variables. Those are, in this case, the 0, 1, 2, and 4. All that means, if it doesn't make sense, is like these values are fixed. They're not going to change, or changing them isn't going to help us solve the problem, is maybe the way to think about it. Our independent variables are the free variables. So these are the x3s and x5s, and these are the ones that are going to allow us to kind of like find a solution with the DP. So you give me a machine, I'm going to do a matrix. I'm going to create the matrix with these values. How do we do that? Well, we add all of our buttons, right, along the row, right, and along the columns. So for each column, we add, and for each row, we set it to 1 if the button is set, right? well, because we're iterating over like the button itself, we're going to set those things, right? So this is saying, this is like in the example, there's only a 3 here, so we're going to set the third position to 1. This one, we're going to set 1 and 3 to 1. That makes sense. We want to add our joltages as the last column. Note that like we never actually do any row manipulation on the joltages. We don't try and solve for those. Those are like the right-hand side of our thing, like in our matrix. So what we're really interested in working on is just like solving this left-hand side, and the right-hand side is what's going to help us get to that like solution, right? So we want to have our joltages there because as we're like dividing and subtracting and multiplying values, we have to do it for the joltages as well. But we don't have to we don't have to do it with the other things, right? Is it clear what's happening here? Like once we've gotten this matrix, like what we're saying is if we use this one, it only affects this joltage. If we use this one, it only affects this joltage. If we use this one, it affects these 2 joltages. And if we use this one, notice this one's crazy, right? If we use this one, it reduces this one and increments this one and this one. And that's how, like, having solved this, it kind of helps you, like, in a mathy way, figure out the values that will get you to the joltages you want. But you have to do the fixing, right? Anyway, so we've created our matrix now. Now we do the Gaussian elimination, whatever it is. So we have some pivot, and this is like the current row we're working on. We're going to start at the top row. We're going to, and we're just going to go down all the rows slowly one at a time. So you can see here at the end, we just go to the next pivot. We'll move our columns though, based on what what button we're kind of trying to fix, right? And stuff like that, right? So you can see we have to track both of those, but the only time we wouldn't move our pivot and our column is if we have a free variable, which is right here. So I'll show you that in a second. But we just want to pick our best pivot for this column, right? So that's me doing this reordering right here. We're going to do it in a loop, but the idea is we're gonna say, oh, this is the best one right now. This is the best one. So I'm gonna move it up to the top and work on it. And then we'll say like, oh, this one's already in the best position and this one is, and then now it's in the right place, right? But at the time you don't know, right? And it is different. So you want to find the best pivot. And then you just check and see, is the pivot value 0? And if it is, then it means where you're currently at, it means you now have like an independent variable. You have a free variable that you can play with. So we add that to our free list and we continue. So we want to stay in the same row because we still want to figure out how to fix this row, but we know that column isn't going to work in this row. So now, otherwise we do our swap to put our best row in that current pivot position, and then we know where we have a dependent variable, right? We found like a 1, and so we know that's one of the dependent variables. So we add that to our list, and then we do the elimination part. And this is just like doing the row subtraction, but it's a very specific way of doing it to ensure you always do it correctly. And it has to do with, well, you can see right here is, if it's not 0, we want to like do some pivot stuff right here. I actually don't think it'll ever be 0. I think I can remove that. Oh, no, we can't because we're doing it over all the rows. Yeah, we can't do it because we're doing it over all the rows. There's rows above us that may be 0, and if they're 0, we can ignore them, right? We want to ignore the pivot and we want to ignore the factor. So that's why those are there. I could probably clean this up a little bit, I think. But we're on the pivot, so we're doing math on the other places. And then we're doing, we may be doing math above that we need to to work on. Okay, so here's how you do that in a rusty way. And I hate this way. But Clippy gets mad at you if you don't do it this way. And so I don't know. This may be a one way where you want to like get Clippy, because it makes more sense to me. Essentially, what this is a for C in column dot dot equals self dot calls, and then you do, you know, a set. You say you basically do this in the thing. You can't Clippy's all like, oh, you're just using that C to iterate over values. You shouldn't be doing that. And so I'm like, okay, well, I'll do it this way. And then it's like, oh, you can't do it that way either. And so this is what you wind up with that Clippy is happy with. But the gist is like you're trying to do first you normalize it, and now you're trying to eliminate all the other values above it and below it, right? You're trying to zero them out. So you do like the row 1 minus row 2, or the row 0 minus row 1. You do like that type of thing to like eliminate all the extra values. It kind of makes the idea is to make them 0. Okay, so that's what you're doing. Again, it would probably make more sense if Clippy didn't tell you I was doing it wrong. This may be a case where you can just, I know that you can do a hashtag to tell Clippy to shut up, and this may be a good case to do that. Anyway, that's the thing. So we're going to do that for each of the rows, essentially how I showed you in the thing, and that's eventually going to give us, we're now going to have a well-maintained, maybe is a good way to say it, system of linear equations, and we're now going to know which of those like variables we can change that will impact the solution. Okay, so now we just have to do that for all of them. So I'm going to go to the BFS I'm going to go to the problem first, and then we'll talk about the other stuff later. So for part 2, what do? I build that matrix and I do the manipulation, and now I can just do a DFS over the solution of that much smaller solution space. And what is that? It's it's the I start at 0 for all of my like free variables, my independents, and I track them here. And so I'm just going to DFS trying different values in this matrix. I'm looking for a minimum value, so I'm going to track my min. And I use this max to kind of help me say, hey, if don't ever go over this, right? Obviously, if like one of the values is 92, there'd be no reason for me to push any button 100 times, right? Like that doesn't, if the highest value is 92, there's no reason for you to push a button 93 times, if that makes sense. So that's what that max is for. But then I just DFS. So what does the DFS look like? Well, like most DFSs, the first thing you check is, are you done? Like, have you reached the end of like your depth first search? So we do that. We say, if our index, right, the one we're working on, is equal to, you know, the length of the independence that we have, the values that we have, then we're going to go check and say, is this solution valid? And if it is, we're going to try and update our min, and then we're done, right? Otherwise, if it's not, we're just going to loop through all the potential values, 0 to 100, right? And so the thing about this is there may only be, I think when I looked, there was never more than like 5 independent variables. So we're never going to do more than like 5 times 100 checks for each one, for the whole thing, right? You're now down to like 500-ish checks or whatever. So that's what makes it small and slow. You still have to do all the math above, but now you have a much smaller solution space to check. So we just try all the values, and then we DFS over, those values, but now try the next one down. And then and so on and so forth and so forth. So hopefully this looks like a traditional DFS if you've seen it before, right? Look for an answer, try all the neighbors, and recursively to see if try the next one down recursively to see if like setting my value to this solves it lower, right? And you just do that over and over again. You could probably, now that I think about it, add, I'm so tired of this problem, so I won't, but you might be able to add a scene list here to kind of help you with your DFS. Although it may not help because we do bounding, right? Obviously, we're never going past max, and then we're also never going past our total, right? So this is actually a big optimization. Is obviously if we've ever exceeded our total, there's no reason for us to continue trying, and so that's a huge optimization, right? But then it's a basic DFS. So what the only other thing you have to do is ask yourself, well, how do I determine if a matrix is valid? And so that's this code right here. And so this function, this is valid, checks your independent variable. Independent. I may have said dependent wrong down below, sorry. We're going to check our independent or free variables and see if it's a valid solution. And if it's not, we'll return none. If it is, we'll return how many button presses would have occurred. And the way to solve that is you basically just go through all the rows of your, you start with how many times you've pressed the total, the independent ones. And then you go through, and this is going to be some large number that's more than you would have actually pressed, right? But it will have, but we can now go through all the rows and subtract all of the dependent variables from this total. No, did I say that wrong? This is how many times I did say that wrong. This is how many times we would have pressed our free variables, right? So every time we click one of the free variables on, that's going to hit these. But we now need to account for how that affected our other variables in that row, right? Or in that, in the row. Yep, in the columns, right? So through the whole matrix, I guess I should say. So we go through each of the rows and we just say, well, what is the value, we go through all the dependents, I guess, right? And so we say, what is the value of this dependent variable based on how many times the independents were clicked? And you had to do some math here, but the idea is kind of like what we had done above is your dependent value may be, I don't know, say because of you did it n times, it's like, let's say it's a 1 or a 3 or whatever, but the free variables would have caused it to click twice. It's no longer 3, it's now 1 or whatever, right? Did I explain that? I don't know if I explained that very well. The idea is we need to do some math here to, like, we have the dependent, or we have the, how do I say this? We have the joltage level, but we need to subtract the free variable. We have the joltage variable for our dependent. Okay, I'm going to try and explain it this way. We have this value right here, right? These are the things we're trying to solve for. We know that this one is x0. This is the x0 one we're interested in. And let's say we're trying 3 and 2, right? So we now know that we're expecting a 2. And we're going to do 3 minus 2 is 1. And we're going to subtract that. That's going to give us a 1, right? So that's what we're going to do. But what if these were like 3 and 5, right? We were testing 3 and 5. Now we get -2 and we do -2. I should do something more. It should be like, it should actually be, what if we were doing 7 and 2, right? And so now we get 5, 2 minus 5 is -3, right? Well, we know that's not a solution. That's not correct. So we know that's not the right one. That's what we're trying to do in this thing. And we want to do it for each of those new equations. So that's what this is doing. So we have to do that check though, right? We have to say, hey, if we're a negative number or we're not a whole number, that's what this part is checking, then we know we haven't found a valid solution. So this is just math, right? We have some epsilon for our floats that's saying, and for mine, I did 1e to the -9, right? So 9 digits of significance. And that seemed to work for me. You probably could do less, like 1 or 2 would be my system. Maybe not that many, but like probably you could probably get away with just doing it a little bit. Anyway, the point is you also want to check this is going to check if it's negative. This is going to check if it's a whole number. So this is saying get the rounded value. We'll use it later. That's why we get it up here. And then we're going to check if the value minus the rounded value is greater than our epsilon. This is just checking if it's a whole number, right? So like if we round up and it's like a 3, and this one's a 3.5, we now get 3.5 minus, let's say 3.4, right? We now get 3.4 minus 3 is 0.4, and that's greater than our epsilon, so we know it's not a whole number, right? It's some half number, so that can't be a valid solution either. I believe you do have to do these checks, right? Yeah, it's not going to solve if you don't check these. Like some of those a lot of these are saying, and remember the puzzle asked you to do this. They're saying if you didn't get these values, if you got a negative value or some partial value, it's not correct. So that's why I kind of am led to believe by the puzzle maker that this is probably the way that you want to solve it. That's kind of what led me there. Anyway, once we've done all this work, we now know that this row has like a valid value in it. So we increment our total. And once we've gone through all of them and we know they all have valid values, so that is to say like all of these equations have valid solutions, we now know it's a potential valid solution. So we return that. And then again, the check up here is to say if we ever get a valid solution, we'll update our minimum. And so we're just going to go through all of our minimums and find the smallest one. And once we've done that, we're done. Okay. Okay, that's a lot of work for part 2. So what do I want you to like get out of this? Maybe you've never done linear algebra before. I mean, you know, there's going to be days that you just don't know how to solve it. If you had asked me to solve this problem, I don't know, 20 years ago, I would not have been able to solve it. But there's other problems. There were days in past where I just had no idea how to solve it. Do you remember the one? There was one where like it was like snow was falling in 3D space and you had to figure out how to like throw a rock to like hit them all at the same time. I was never going to solve that one. I just knew it was too mathy for me to like ever solve it. And so that's when I learned about the Z3 solver. It just occurs to me that I think you could solve this with Z3, right? Oh, bugger. Yeah, I think you could solve this with Z3. You probably don't even have to do this. You essentially what you're going to pass to Z3 is this matrix, and then you're going to try and solve it. Tell it to solve it, and it will solve it for you. Man, I bet you there's solutions that solve it with Z3. Okay, well, I did all this work, and now I think you could probably solve it with Z3. Though I will say, did we talk about Z3 in this solution? Have I already forgotten? Anyway. Yeah, I think you could solve this with Z3. Did I not think about that before? Man, I've lost my mind. Anyway, the point of all of this is to say there were days that I knew I just couldn't solve and I needed help. If you need help, go get some help. So I got the little AI to like help me out with this. I think I did some math here and I said, okay, I think what I have to do is this. Is that right? And they're like, yeah, you got it. Good job. Like, here's what you can do next. And I'm like, okay, then I did that and I get this. So does that make sense? And they're like, yeah, you're right. You did it. Good job. So that was me kind of working my way through like it gave me a hint and I tried to figure it out. And then like I said, hey, am I going down the right direction? And they're like, yeah, you're going down the right direction. You need someone like that, right? Maybe it's looking for other answers to like in the solutions space. That's totally fine. Sometimes you're just not going to be able to solve it and get some help. So that being said, let's go look and see. There you go. Exactly. Z3, the very first one. Yep. You do all the presses. You minimize the presses. Yep. Okay. Totally a Z3 answer. I wanted to look at Paulson's. I always kind of search for him to see. Use brute force for P1 and Z3 for P2. Yeah, there you go. Okay, everyone use Z3. Egnabbit. We're live. Oh, we're just keeping for each line. We're keeping track of the solution for part 1 and part 2. So part 1 you can see is kind of just using a wow, this actually is like a brute force. Yeah, you literally just brute force it. Again, I think that for part 1, the solution space is small enough that you totally can. And then they use Z3 here. Yeah. Yeah. Okay. Very good. Let's see. Linear programming library. Let's see. Micro LP. It did occur to me that it might be interesting to use a linear program. I think there's like N algebra. I haven't heard of this. I just don't do a lot in this space, and so that's why I just like I'll just solve it. Micro LP. Is this kind of like a Z3 solver, but like very specific for like linear algebra problems? Okay. Yeah, this just solves. My thinking is like the reason why it was used is you can say, um, oh, it's interesting everyone used brute force here, and my BFS solution feels like it solved it pretty fast. Yeah, it's slightly faster. Used a linear programming library. This is I would like to learn more about these linear programming libraries. Like it looks like what it's doing is like for specific linear algebra problems, it will help you find the solve. So like what's happening in the code here is um you add all your buttons, you add the button masks. Okay. That's kind of cool. Oh, did they use a yeah, they did use a indicate again. Using the bit mask seems to be a fun optimization, I think, in Rust. right? You could just use a vec bool, but I guess there the Paulson solution also used, yeah, you see here they use a bit mask. Okay, let's see what else do we got. Home cooked linear algebra, no external libraries. I just saw like reduce, row reduction, bag substitution, check about 3 parameters. Sure, at most 4. Was there? I swear I saw one that was like 5, but it's still small, right? Comparatively small. I mean, this is just going to be what I do. Although I should say I use Gaussian elimination. I believe there's like there may be faster ways to solve. I just don't know them. The Gaussian one I know because it's very stepful. Like when I've taken 2 linear algebra courses. One was like the actual math one, and one was like writing programs for linear algebra. And we just did the Gaussian, and it was easier for me to remember that one anyway. So Z3 SciPy to solve it. XOR is 1 for part 1. Okay, good. Today I learned why Python is IRAP LP. These, as opposed to Z3, these ones must be specific to like solving linear algebra. It's a known thing. That's why when it said, "Oh, this is you've gone from a what did it say? You've gone from a BFS to a whatever. Oh, graph theory to linear algebra." I was like, "Oh, okay. I think I can figure out how to solve this if I just think through it a little bit with the AI." That was the thing, is like I didn't get there, but yeah, I and so knowing this stuff, especially these ones, are kind of cool, right? Like if oh no, what was I looking at? Like this one, a linear solver, that's cool. There must just be libraries that like specialize in solving linear systems of equation. Yeah, so like I think this is exactly what I was just saying, right? Is like if you know it's a system of linear equations, like obviously Z3 can still solve for that because it's a generalized solver, but you can also just use a specific, linear algebra solver for part 2, and that works. Z3, lots of Z3s. We look for rusts. If I can speak, if I can type. Use linear algebra solver. Okay, for part 2. Let's go look and see. What do they use? Oh, micro LP as well. Okay, this is something I'll have to learn about because I think it'd be useful. Yep, XOR. I was really, you can tell I'm frazzled. I was like, wait, why is that not working? Part 2 is not solved by code. Z. Okay, there you go. Yeah, Z3. I don't think, if there was only one of these and it was very hard, you might be able to solve it by hand. But there's like 100 of them, and so I can't imagine solving 100 of them by hand. Yeah, we got a lot of people doing the binary representations. I don't know, we're all on this binary kick. It's kind of fun. I think it's nice because it's helping me remember all the binary stuff that I learned a long time ago. Like this one I actually did part 1 on my own with no help, which I guess the bitwise stuff. Often I have to like look up like bitwise flip a bit or something like that, right? And I was like, oh, I know how to do that now. I can XOR it. Things like that, right? I don't like look for the solution, I should say. I like look for how do I do this in Rust or whatever. DFS with memoization. Oh, see, I'm curious how much faster a DFS with memo runs. That is so. I do find again sorting helped, and when I was doing my DFS, I purposefully sorted, and then I went because I was thinking, oh, if I sort, I I prefer to check like the higher ones first, and maybe it will have like I'll have like seen a solution before, and I won't have to like flip the zero a million times and then flip the one a million times to get to the thing. So that's but then when I went to remove it, it suddenly made my part two slower, and I'm like, wait, why does sorting help? And I think it just like puts them in row echelon form faster. I don't understand why that works. But this, yeah, I didn't even do DFS for the first one. Yeah, if you're gonna do straight up DFS, you have to do a lot of pruning, right? You can see I already did with my DFS. I still have to do pruning, right? Obviously, I want to stop when I've reached an invalid value, like if we have some invalid solution or we have an invalid, um, like we've gone over our target and stuff like that. Get the buttons that affect the jolt value. Okay, so these were things that were occurring to me as I was trying to optimize my DFS before I like just kind of gave up. So this guy kept at it, and I think that's cool. I wish maybe I should have stuck with this, and even if it takes 8 seconds, I solve it. But like I think it's these like, can you make some micro optimizations is what I kept saying, is how many optimizations can I make to this? And I'm like, maybe I will just never be able to make enough and I can't DFS. But apparently the answer is yes, you can. So if you make enough, you can solve it. And is 8.5 seconds optimal? No, but it's cool that you DFS'd it yourself. I tried it, I couldn't DFS it, so I just gave up and tried, and looked for help. Man, I probably should have kept at it. I would have gotten there, because it's not. If you think about like what I was DFSing, it's not dissimilar to this, but I was just probably missing some of the special optimizations. Yeah, like this one. I think this is the one that I was kind of thinking about. Is like, can we prefer to pick solutions that like um have the most effect on the joltages? Like that was the thing that was going through my mind. Is there some way for me to like algorithmically pick that? So very cool solution. 3 hours and 40 minutes to run. Spit out the correct answer. Okay, that's a crazy solution. I mean, if it solves, it solves. That's what I'll say. Some people have said, "Oh, I did this, but it was like 3 4 loops, and it was like n cubed times n squared to solve it, and it took 5 minutes to run." You solved it, dude. That's awesome. That is cool. Believe in yourself. Uh, Part 2 Z3. Good LP is an LP wrapper. Yeah, I think this is an interesting one where it looks like we can just use actual linear algebra solvers that I don't know. Again, I think I've used Z3 like twice now, maybe 3 times. I don't think I've ever used any of these linear uh, algebra solvers. I think it would be fun to research, because you'll see that it comes up like once or twice a year in all of your puzzles. You suddenly have to know these things to solve it effectively. And that being said, it's just that we all find out that that's like the easiest way to solve it, and so we do that. It's still possible there's some trick in the puzzle input. I looked for a while. I'm like, oh, what if can I find like, I was really focused on this bottom one, and then I tried a couple others. I'm like, oh, if I do like this one and this one, does that like cover notice like this one's 18. So like I'm asking myself, is there a 6 somewhere that I can get all of the 18 from? And so that puts the oh, it's right here, right? And so that's going to reduce this by 18, right? So now it's 72. So now I have, I'm going to do that one 18 times. Now I look for the smallest one again. It's 32. So which of these affects that? I'm going to reduce all those. Like that's the solution I was trying to do with my DP, I think. And it just wasn't solving. So it may be that I'm a bug, but that was kind of what I was trying to go for in the puzzle. Like, is there something special about the input? That is to say that these things are carefully crafted in such a way that you don't have to do like a generalized solution, but you can do a very specific solution to get to it. I could just never find it. So notice too, and like the reason I say that is because notice like the biggest number has an incrementer right here. And so I suspect what happens is like you do all this work and eventually you get to, oh, I still got to do 2 more of these. And then you just press this 2 more times and you're done. I could never figure it out though. So it'll be one that maybe if we have time we can go back to. Okay, let's look at some memes. Me with NumPy not knowing what Okay. Yeah, Z3 helps a lot, but I know there are some like, I don't know, purists that are all like Z3 is dumb because you'd basically just solve all your problems with Z3 and stuff. I don't actually think that's the case, but some people think like Z3 is a weird thing, and the thing is like if you know linear algebra, like sure you could solve this with linear algebra. If you don't, the next best thing is probably Z3 because you don't actually technically need to know linear algebra to solve Z3. It helps because it helps you like format the problem so that you can use Z3 to solve it. But you can kind of infer like, okay, here's the buttons that get pressed at each state, or here's how each button press affects the state. And then here's the state that I'm looking for. Now minimize the number of clicks of these, minimize the number of these to get to this. And Z3 will figure that out for you. Yeah, we all knew what was coming. For part 2, I was like, oh, we're going to use those joltages. How are we going to use them? I didn't think too much about it, but I had sort of suspected that it would be I don't think I didn't suspect it would be what the problem was. I sort of thought it meant like it was going to have some effect on like how the lights turn on. And so you'd have like a second set of like your solution space would expand because of like how you're doing it, but you could still potentially BFS or DFS to get to it. So that was going through my mind. Not this, which was like a linear algebra nightmare for me. Yeah, you can't press the negative buttons. It would be nice because that would help a lot, right? You could solve the problem really easy. Part 1 Whopper. What is this? They're using like the Whopper code to do it. Got the correct answer after 6 hours of brute forcing. Oh, this is cool. There you go. Let it run for 6 hours. That's what I didn't do. I didn't let I actually par itered it too, par bridged it. And yeah, I actually par itered it to see if that would help. Watched my computer heat up my room. I just didn't think it would ever finish. Apparently, it might have finished in about 6 hours. Yeah, definitely depending on how you, if you just, it's one of those days where if you just try and solve part two the normal way, not easy. Oh, you had a, oh, what was there, what were they thinking the solution would be? Yep, I tried that too. I'm with you, brother. Uh, wait, what did that P2 is of similar difficulty part with the buttons update the same number of indicators? I don't think that's quite true. I mean, yeah, seconds to hours is more like it, right? I spent a lot of time on part two, again because like here's the thing you don't see, and I feel better about doing these recaps more like this than like watching you solve it. When I was like, okay, I'll just try the BFS, that one didn't take long because you're basically just changing the the bit mask that I had set up to be a vec of U size, and then you're incrementing and decrementing it. I even like made it mutable so you increment and decrement as you're going through the solution, so you don't have to make copies. Um, and it just I had never solved the first one, and I'm like, oh, there's 100 of these, and even if the first one takes 10 minutes, that's like way too much time. So I kind of stopped with that. Then I tried the DFS, spent some time. I think I could get the DFS had solved like one or two of them, but then it was stuck on another one. And I don't know if it was that it was like bugged, or if it was I was missing something, or it was just that one happened to be the one that was like bigger and so made it impossible to solve. And I then anyway, so this is all to say I spent a bunch of time on this, several hours. Where are we at? It's 2:30 where I'm at. I started at 8 and worked on and off till like 1. So obviously I'm at work doing work, but as I have time, I spend 20 or 30 minutes, go back to work, then 20 or 30 minutes. I was also in a meeting for a couple hours where I was like, I'm just gonna okay. Day 9 part 2, day 10 part 2. These were hard days. I've already put day 9 out of my mind. What was day 9 about? Wait, it's coming. Oh, I did the prefix sums, the 2D prefix sums. Yeah, that was a hard day too. Yeah, I think we're definitely in the hard day category. And just to be clear, like there were years before where the hards I couldn't solve. Yeah, I think, well, I kind of felt this way. I got help, so I felt you can replace the Z3 with Google or Gemini, I guess. I feel dirty. I I'm personally of the opinion that if you got the star, you got the star. And as long as it wasn't just like, oh, I copied a bunch of code, like I think you're cool. If you had to copy some code to figure it out, but you like read it and understood it, I think that counts. It's just if you're just all like, oh, I'm gonna type the problem in AI and say solve this for me, and then I'm gonna submit it and be done with the day. Like that doesn't net you anything, right? But if you used AI to help you like figure out problems or find bugs, and then you understood why your bug was a bug, you've grown from this, and I think that's cool. So trying, that's what I'm hoping you get out of all of this stuff. Is just keep trying, looking for hints if you can't solve it. You know what I mean? Do your best. And if you were struggling immediately on day one and you're like, you're still getting to these things, maybe it's like 2 years later, you're still trying. I still have unsolved ones, right? 1 year. In fact, you can probably see it on here. Oh, maybe you can't because of the way it works. This one, 2019. No, wait, is this the right one? Oh, this is the int code. I haven't finished. Yeah, I did not finish these int code ones in real life in 2019. We've done some of the int codes, but I have not finished these two int code ones in I did not finish. You can still see this is my real one where I have like most of my stars. I did not solve these days. I could not figure out how to do the int code with these. So I think a lot of these ones, this one I believe is a network one. Yeah. And then this one is, maybe I have since figured them out because I was doing a video series and I may have solved them. But at the time in 2019, I could not figure out how to solve them. And so it just to be clear, it can take years to like eventually you've learned enough that then you go back to a problem and you're like, how is this ever hard, bruh? Right? So just keep working at it. You'll get better. Hopefully you get that out of this video. I will fully admit that I am weak in like the linear algebra category, and so for it to get me to, hey, solve it with a linear algebra, it took me a while to I didn't get there. I need the hint to say try linear algebra, and then I could say, oh, I remember doing the Gaussian elimination, the free versus fixed, or independent versus dependent. And then now I think I can solve this. Okay, but I definitely spent a lot of time trying to figure out how to do it and get it to work. But I don't think if you had asked me this question 15 years ago, I would have had any idea. And I don't think they had a Z3 solver 15 years ago. It may just not have been possible to solve, at least in my mind. I wouldn't have been able to, much like these ones are not solved. So I don't know how many ways I keep saying this, but just keep trying, keep learning, keep growing. If you're doing that, I'm proud of you. Keep it up. And I'm going to keep doing it too. Hopefully you enjoy these videos, and I think we'll call it a day. So thanks, everybody. Talk to you next time. Bye.